to Anna Balibanu's talk on perverse sheaves and the cohomology of regular Hessenberg varieties.
Thank you. So I want to thank the organizers for the opportunity to speak. And also because this is the last talk, I think we should thank them for organizing such a nice and successful and engaging conference. So I think I can hijack. Yeah, so everyone can unmute themselves and like give a round of applause to the organizers, please. Okay, great. So I also have had really wonky internet for the last few days, and it hasn't happened yet that it's failed while I was speaking, but I did get kicked out of the Zoom meeting like 4 times during Ben's talk, so just a fair warning. And I have at least 2 backup devices that I can hotspot to, so hopefully everything will go smoothly. Okay, so my talk is about the cohomology of regular Hessenberg varieties, and this is joint work with Peter Crooks. And I want to start just by setting up some data. So my group G will be semisimple, simply connected, and complex. And I'll fix a maximal torus and Borel for the rest of the talk. And I'll use fractal letters to denote the algebras. And then I'll call H a Hessenberg subspace of the Lie algebra if it satisfies these 2 conditions. So it should be a module for the group B, and it should contain the Borel subalgebra. So examples, obviously all standard parabolics. But there's no requirement for this H to be a subalgebra. So I can also have things that look like an SL3, the Borel, and then the negative simple root spaces. This is also an example that will recur. And then because H is a B module, I have an associated bundle over the flag variety. And it comes equipped with a map to the Lie algebra, applies G to X via the adjoint action. So this is a proper family, and in fact, this vector bundle, its total space has a Poisson structure, which I won't really give details about. And this mu is a moment map for the left action of the group. Okay. So if we fix S in H, then every element in the Lie algebra is going to have an associated Hessenberg variety, which is just the fiber of the small telling me that my internet connection is unstable, but that this still works. Anyway, so I think of the Hessenberg variety associated to X as just being the set of cosets GB, so that when I apply G inverse to X, I land in the Hessenberg space H. And a couple of facts is that when X is a regular semi-simple element, its associated Hessenberg variety is smooth, and in fact more is true. So all of these are isomorphic, and the restriction of mu to the regular semi-simple locus is a smooth morphism. And when X is regular, all of these Hessenberg varieties have the same dimension, which is the generic dimension equal to the dimension of H mod B. And mu restricted to the regular locus is flat. So a couple of examples. First, extremely familiar example is the Springer simultaneous resolution. And here the Hessenberg variety associated with point X is just the growth index Springer fiber. This is just a collection of Borels that contain X. And in fact, for any Hessenberg space H, because I required H to contain the Borel, I have an inclusion of vector bundles between the growth index Springer resolution, or from the growth index Springer resolution, and this universal Hessenberg bundle. And And this inclusion commutes with the moment maps. So I always get the growth in Springer fiber living inside the associated Hessenberg variety of X. And in fact, when X is regular, we can be more specific, and we can recognize this fiber as exactly the points of the Hessenberg variety that are fixed by the action of the centralizer of X. And this is because a regular element is contained in a Borel if and only if its centralizer is contained in a Borel. If and only if its centralizer fixes that Borel as a point of the flag variety. Okay, so slightly less familiar example. I take H to be the direct sum of the Borel and the negative simple root spaces. So in this case, for any regular element, its Hessenberg variety has dimension equal to the rank of G. And its centralizer also has dimension equal to the rank of G. And I always have this centralizer acting on the Hessenberg variety, and in fact, this action was with an open dense orbit. So for example, when S is a regular semisimple element, its centralizer is a maximal torus. I expect this Hessenberg variety to be a smooth projective toric variety. And these are indexed by fans. And the fan of this guy is the fan given by the Weyl chambers. I drew the SL3 picture. And then when E is regular and nilpotent, I also get a sort of familiar face, which is something called the Peterson variety. Now, it doesn't matter exactly what this is, but what I want to say about it is that it's, except in very small rank, it's singular and generally not normal. So even on the regular locus, these fibers can get sort of complicated.
Anna, you want to try turning off your your audio is coming through a little choppy. Sometimes turning the camera off helps with that.
Turning the camera off.
Yeah.
Right. I also don't hear you very well. Okay. Let's try this. Yeah, someone already suggested this in the chat too, so thank you for that. I would tell you to like alert me if something bad happens, but it's like, it doesn't really work that way, because if something bad happens, I won't be able to like see or hear any of you anymore. But anyway, so is there anything that didn't come through in the last couple of slides that I should repeat because I wasn't audible?
I think it's okay.
Okay.
And maybe it was just my computer, but someone else did mention it to me, so it wasn't just me.
All right, so back to the general setting. I have this Hessenberg space H. I have its associated bundle over the flag variety. It has a moment map, and I'm interested in the fibers of this moment map. And the sort of philosophical goal is to understand their geometry, whatever that means. So I want to start out with the simplest case when I take a regular semisimple point, and its centralizer is going to be this maximal torus that I fixed, and it's going to have an associated Weyl group. And when the centralizer acts on the regular semisimple Hessenberg variety, it makes it into what's called a GKM variety. So this stands for Goretzky, Kottwitz, McPherson. And what we need to check for this to be true is we need to have finitely many fixed points under the T action. And we need to have finitely many one-dimensional orbits. So in general, for a GKM variety, you also have to have something called equivariant formality, but these guys are smooth, so they're automatically equivariantly formal. And then what happens if you're a GKM variety is that your equivariant cohomology has special properties. So the specialization map that goes from equivariant cohomology to regular singular cohomology is surjective. And the pullback that goes from equivariant cohomology to equivariant cohomology of the T fixed points is an injection. And now, of course, equivariant cohomology of the T fixed points is just equivariant cohomology of the growth in Dieck-Springer fiber. And this is a finite set of points indexed by the Weyl group. So this looks like a sum of Weyl group many equivariant cohomologies of a point. And this looks like a sum of Weyl group many coordinate rings of the Cartan. So using this diagram, there's something called the Tomachko noticed that the Weyl group is going to act in a natural way on equivariant cohomology of these fixed points. Action here. So the idea is that the Weyl group acts on this coordinate ring like you'd expect, and it also permutes the summons. And then Tomachko showed that this Weyl group action restricts to an action of the Weyl group on equivariant cohomology of the Hessenberg variety, and then descends to a Weyl group action on the singular cohomology of the Hessenberg variety. And the sort of question to answer, or at least answer partially, is which irreducible representations of the Weyl group appear in this action. So this question is already answered in type A when G equals SLN. And this is because in type A, this is a question about a particular representation of the symmetric group. And it actually has many applications to combinatorics, which is why many people who study Hessenberg varieties are interested in them. And the way that this question is answered for the symmetric group is that the character of this representation is identified with a combinatorial object called the chromatic quasi-symmetric function of a particular graph. And then it's known how to decompose this polynomial into summons that correspond to irreducible representations of the symmetric group. And then by this identification, you can come back to this Tomachko dot action. And but in general, this question is sort of open, and we can use this observation that I'm about to state to give a kind of reinterpretation of it, which makes it possible to answer it at least partially. So remember that when I restrict this moment map mu to the regular semisimple locus, I get a smooth vibration. And the Hessenberg variety of S is the fiber above S. So this means that that I have a monodromy action of the fundamental group of the base on the cohomology of this fiber. And I also have this Tomachko action. And what Brosnan and Chow, who sort of answered this question on type A, what they observed is that these two actions are the same. So there's a surjective map from the fundamental group to the Weyl group, and the action factors through this map. Civil representations, we can use sort of the decomposition theorem and the formalism of perverse sheaves. So what this decomposition theorem tells us is that if I take derived push forward of the constant sheaf on this total Hessenberg family, so all my push forwards are derived, but maybe this is the only one that appears in this talk, I get a sum of irreducibles in the derived category, and I've separated them into irreducibles with full support and irreducibles with that are supported on smaller strata, which I won't care about. And this observation of Brosnan and Chow, it tells me that the irreducibles that have full support are indexed by irreducible representations of the Weyl group. Monodromy representations that factor through this map. So instead of, well, I can reformulate my previous question and ask which irreducible local systems appear in this decomposition. And I can answer this question by using the Springer correspondence. So the quick reminder is that the Springer correspondence takes an irreducible representation of W and associates to it a nilpotent orbit in the Lie algebra and an irreducible local system on that nilpotent orbit. And our first theorem is that if I take H perp to be the annihilator of H under the killing form, so remember that H was supposed to contain B. So this means that H perp is contained in the annihilator of B, which is its null radical.
I'm seeing a lot of comments in the chat that your slides seem not to have changed. I'm still seeing the one with the observation of Brosnan and Chow.
Oh, no. Yes, you're right. That hasn't changed. Let's try this. Okay. Troubleshooting. Great. Thank you for telling me that. Let me backtrack then. So this is the one that we were stuck on. Is that right?
Yeah, that's where we were stuck.
Assume so.
Yeah.
So this is maybe and then what the slide contains is this is the one that we were stuck on.
No, we haven't seen this one yet.
Okay, so could you see the slide while I was explaining it?
No.
Let me briefly recap. Sorry about that. So the moral is that this Weyl group action, which was constructed in this totally combinatorial way, is actually a sort of geometric action that comes from monodromy, and then this means that we can address all of these questions in this decomposition theorem setting. So if I take the decomposition of this derived push forward, then I get sort of two halves. I get one portion that has full support, and I get another portion that is supported on smaller strata. And I'm only going to be interested in the first one because what happens is that the fact that the monodromy action factors through the Weyl group tells me that the irreducible local systems that appear with full support are actually indexed by irreps of the Weyl group. And now the question is to determine these irreps. So, okay, so now we're here. So we're going to determine these irreps using Springer correspondence, in which I recalled over here. So to every one of these local systems indexed by an irrep, I associate a nilpotent orbit and an irreducible local system on that orbit. So what I was doing before it was pointed out that no one could see what I was doing is I was explaining that if I take my Hessenberg space, I take its annihilator under the killing form, I will get a subspace of the Lie algebra that is contained in the null radical of my Borel, so that contains only nilpotent elements. And the theorem is that if a local system indexed by an irreducible representation appears in this monodromy action, then the corresponding nilpotent orbit intersects this annihilator. So probably at this point I have like 6 minutes left, so maybe I won't say very much about how this is proved. And instead I'll move on to the question of more general regular elements and what we can say about the cohomology of their associated Hessenberg varieties. So what I want to do here is I'm going to apply the local invariant cycle theorem to this setup. So remember that when I take this moment map mu and restrict it to the regular locus, I get a proper flat family where the generic fiber is smooth and the special fibers are who knows what they're like. And if I have a regular element, I take its Jordan decomposition. By conjugating, I can always assume that its semisimple part lives in this carton. And this means that it has a stabilizer under the action of the Weyl group. And again, by conjugating, if necessary, I can pick a regular element.
But we're still seeing the slide with your theorem with Peter at the bottom of it.
Goodness. Okay. Sorry about this. Now you're seeing the right slide. Is that correct? We moved.
Yeah, that looks better.
That looks better. Okay. I don't know why this is. Normally this happens if my iPad screen falls asleep, but it isn't doing that. So it must be something funny about my Wi-Fi network, probably. Sorry about this. Anyway, so the plan is to use the local invariant cycle theorem. So we have this regular element. I made a Jordan decomposition. I assumed, without losing generality, that the semisimple part was contained in the carton. And I use this notation to denote its stabilizer in the Weyl group. And then I take a kind of nearby regular semisimple element that, again, I can assume is contained in the carton. And then local invariant cycle theorem tells me that I always have a map from singular cohomology of my special fiber to singular cohomology of my generic fiber, whose image is some local monodromy invariance. And in fact, one can show that these invariants are actually, and the proposition, which was proved by Brosnan and Chow in type A, but which one can prove generally, is that this local invariant cycle map is actually an isomorphism. So, so what this does is it lets us sort of get a hold of the cohomology ring of the Hessenberg variety associated to, in general, a singular projective variety, and as a subring of the singular cohomology of a regular semisimple Hessenberg variety, which is smooth. And the theorem is that using this one can show that this sort of special Hessenberg variety has what people call the Kahler package. So it has Poincare duality and the Hard-Lefschetz property and the Hodge-Riemann relations, which we'd expect from a smooth projective variety like Hess S, but which we don't automatically have for a singular one. Okay, so I hurried and now I finished 2 minutes early. So thank you.
All right, so people can unmute themselves and ask questions.
Can I ask, so for cohomology of Springer fibers, one can deform the W action to the Hecke algebra action and also a fine Hecke algebra action. Is there something like this here?
There's something that I'm interested in, but I haven't really had a chance to think about yet.
Okay, thanks.
I mean, in general, the W action on the Springer complex is a bit different because that's coming from like the it's coming from the fact that on the regular semisimple locus, that's actually a finite cover. So it's coming from deck transformations. Mm-hmm. This is really a monodromy action. So it doesn't extend to a Weyl group action on non-semisimple fibers. There's sort of many questions like which things that people do with Springer fibers, which games you can play in this setting, and this, of course, all of these questions are interesting.
And maybe another question. So if you consider the K groups, a Grothendieck group of coherent sheaves, is that known to be isomorphic to homology in this case, like analog of. That's usually checked for Springer fibers by this work of Decomposition, Lustig, and Procesi, which have paving for Springer fibers, but here it's more.
So there are affine pavings for some Hessenberg varieties, but not for all of them. Problems as in the Decomposition, Lustig, Procesi situation. In a levy, then it's not known. It's like vanishing on cohomology.
Thanks.
I have a very random question. I don't know how combinatorial this cohomology of Hessenberg varieties has become, but is there a chance of there being an analog of this for other Coxeter groups?
What does that mean?
Well,
an analog of this for...
Right. I mean, you've got the analog of the symmetric algebra of the torus or whatever is just the symmetric algebra, the reflection representation of a Coxeter group. And a lot of the stuff that's done with Perverse sheaves on at least 5 varieties has analogs for Coxeter groups that are completely combinatorial or algebraic. I just had no idea if anything of this, like it's still got a braid group. It's still like all this geometry doesn't exist, but analogs of a lot of it. So I just didn't know if there was a.
I don't know the answer to this question, but probably there are people who are really like very familiar with the combinatorial side who could answer it better.
Okay, thanks.
I have a question. There's this presentation of the cohomology of the Hessenberg varieties as a quotient of a polynomial ring. Can you say anything about what the Kahler class looks like, just in terms of this quotient, or just in general?
I'm not sure. So I guess the Kahler class, I believe, is really the Kahler class that's being restricted from the Kahler class of the flag variety. Maybe yes. So this is like definitely true. So I'm not sure what you're thinking of.
Yeah, I guess that's
maybe.
Oh.
Does that answer your question? I'm sorry, I hear everyone in a sort of choppy way, so maybe.
Yeah, no,
maybe I'm gonna stop my sharing.
That's definitely helpful. Thank you.
Okay.
I have a short question. Can I ask a question? So is it immediately obvious that it's clear that the braid group would act on the homologies, but why is it obviously clear that it factors with the Weyl group? I know it's fact, but is it easy to see? And related question to that, if you have the guys which come from the smaller support, is it true for them that you always have action of some braid group? Is it true that action would factor through the finite dimensional Weyl group?
So to see that this action factors, what you have to see is that it's sort of, you have some kind of monodromy action also in equivariant cohomology, and
okay.
And you have that the action is factoring there, and then it's sort of automatic because variant monodrome action induces the usual monodrome action, and this like Weyl group action induces this topological dot action, and then you just know. About the local systems on other strata, I really don't know, and I also don't even have like a good idea of how to get like a handle on them. But I don't know. Yeah, I don't know the answer to that part of the question.
All right, thanks. Yeah.
So I was just going to suggest that we also do a round of applause for all of the speakers. I think it just switches to whoever claps the loudest. So, thank you for whoever was really putting their heart into it. So, as I said before, I think we'll try to have a more informal meetup in room number 1 as numbered in the emails. I'm still having this weird problem where I can't paste into chat. So if someone else wants to paste the link into chat, they should feel free. Thank you. Thank you, Andre. And yeah, please remember about the survey, and thanks so much for coming to the conference.